We're going to continue 10.2 talking about Cartesian equations for conic sections. So on day 1 we did 2 examples. Example 1 of an ellipse, example 2 of a hyperbola. And today we'll do a few more examples. So on my notes I'm just going to write that this is day 2. And I'm going to do 3 examples with you today. So example 3. Let's see, what does it say? It says to sketch the graph of x equals 6 minus 1/2 times y minus 2 squared. Okay, so the first goal here is to figure out, well, exactly what conic section do we have here? And you notice that only one of your variables is going to be squared. So all of our conics, a circle, ellipse, hyperbola, all have 2 terms that are squared, or 2 variables that are squared, except for the parabola. So the parabola has, you either have y equals x squared or x equals y squared. Now we are dealing with an x equals. This is an x equals. Therefore, I know that this thing is going to open in the x direction. So I'm going to write down this general equation. So because it's opening in the x direction, notice that the x and the k and the h have been switched. This is still going to be your horizontal shift, and this is still going to be your vertical shift. It's just that now the k goes with the y because that's your vertical shift. And the h I could really bring over here and make it x minus h. And so that's going with the x, so that's our horizontal shift. Okay, so we know that this opens in the x direction, which basically means it sits on its side. We're used to them opening up or down, but this is going to actually open to the left or to the right. Okay, in addition to that, let's see, we know what our h and our k are. So we have our vertex. Well, my h now is in front, or it could be on the other side too, or like I said, it could be subtracted to the other side, of the whole equation. But our h is basically 6, and our k is 2, so we know that that's where our vertex is. This is basically going to be opening in the x direction, so instead of having an axis of symmetry that is vertical, our axis of symmetry will now be horizontal. So our axis of symmetry, instead of being x equals something, is going to be y equals whatever the y equals to. That's a horizontal line. There's one more little key thing here that we need to think about, and that's our a. So our a here is 1/2, but it's a negative 1/2. So this is basically going to be a reflection in the line, reflection in the y-axis. Normally this would be a reflection in the x-axis, right, if it's y equals. So if it had been opening up, it's going to now be opening down. However, because it's x equals and this thing is basically opening in the x direction or turned onto its side, it's now going to be reflected in the y-axis. So normally these things will open to the right, and now it's going to have it open to the left. So this is a reflection in the y-axis. Okay, and then I'm going to just start graphing this. So again, my vertex is at 6, 2, but that's pretty much as far right as I'm going to have to go because it's going to open to the left. so the first thing I'm going to do is I'm going to graph the vertex. From there, I'm going to find some more points. So I'll just do like a little input-output table. And I'll make this as easy on myself as I possibly can. So a really easy input here would be maybe to plug 0 in for y. So I'll plug 0 in for y, which is going to make this -2 squared, or 4. Negative a half of 4 is -2, so 6 minus 2 will give me 4. So 4, 0 is also going to be a point. Now my axis of symmetry, like we said, was going to be at y equals 2. So I'll go ahead and put a little dotted line there for my axis of symmetry. Which means that anything that's on the bottom of that line will be reflected and be exactly the same on the top. So 4, 0 is a point, but so will 4, 4 be, right? Because that would be symmetrical. Okay, so 4, 4 is going to be another point. And this is good, you know, by plugging 0 in for y, I get my x-intercept. I'm not going to, it would be pretty tricky to get my y-intercept because I'd basically have to plug 0 in for x and then solve for y. I'd have to do some square rooting. So we'll just stop there. I think that's good enough. Get your vertex on there, get an x-intercept, and I think we're good. If it was opening up or down, go ahead and try and get your y-intercept instead. Okay, so let's just say it looks something like this. Oh, I didn't go through that point, but good enough. Okay, let's do another one. So this is going to be example 4. And this is actually on page 502 in your textbook. I did not make a copy of these for you, so just open up to page 502 in your textbook. I'm going to do that right now. So here's example 4. And the directions here are to find the particular equation in center radius form for the hyperbola in this figure. So the one that's on the left. They're actually the same, but this will kind of help us as we go along. But here it is right here. And I can see that it's a hyperbola that opens in the x direction. So the first thing I'm going to do is I'm going to look for that equation. So basically, oops, hold on, I gotta get back on the screen here. I'll toggle back and forth. So if it's opening in the x direction, then that means that the x squared coefficient is going to be positive. So I'm basically going to use this equation right here. Okay, so I'm going to write that down so that way we have that to look at. So I'm going to use the x minus h over the dilation factor of x squared minus, and so now the y is the negative term, because it's not opening in the y direction, and then we'll set that equal to 1. Okay, so we get the dx and the dy basically by figuring out the x and y dilations, and that comes from the asymptotes of our slopes. Okay, so why don't we spend a minute looking at that? Let's find the asymptotes, or let's find the slopes of our asymptotes. Sorry, a little bit tired right now. So if I look on my screen here, the asymptotes of the slope, or sorry, the slopes of the asymptotes, darn it, are basically, you know, if you just choose any 2 points along these asymptotes, and I'm looking for exact points, so this is a little bit tricky. Let's see, let's go 1, 2, 3, up 3, and then over 1, 2, 3, 4, 5. Okay, and I'm just going to check that. They actually did that over here for us. So going from the center and going along this positive slope asymptote, we're going to see that it actually is 1, 2, 3, 1, 2, 3, 4, 5. I should have my glasses on. I cannot see these very well. But anyways, my asymptotes, the slopes of those are going to be positive and negative 3/5. So let me write that down. So that's going to help us with putting in you know, for d sub y, it's going to be 3, and for d sub x, it's going to be 5. Okay, the other thing I'm going to need to know here is my center, because my center is located at HK, right? So let's figure out my center. I think we figured that out last time when we were looking at it. But my center appears to be -4, 2. Yep. Oops, I'm writing and you guys can't see that. Sorry. -4, 2. Okay, so this is basically going to be my H. This right here is going to be my K. This right here is going to be my d sub y, or my dilation factor of y. This is going to be the dilation factor of x. And then I just go through and I plug it into this equation. So I'm going to have, let's see, x minus -4 will give me x plus 4 over 5 squared. And then subtract, and then we're going to do y minus k, which is y minus 2, over my dilation factor of y, which is 3. Square that and set that equal to 1. And there you have it. Okay, I'm going to do one more problem with you guys for today's lesson. See, I think I'm just going to use regular paper. We're not going to do another graph. So our last example for today, example 5. This will be page 503. Similar type of problem. So they're going to give us a graph, and we're going to have to come up with the equation. Now let's find it. So here it is. Alright, so we're going to find the particular equation in vertex form for the parabola. So once again, it's a parabola opening in the x direction. It's like a parabola on its side. So, showing you my thought process here. So it's a parabola opening in the x direction, so I know I'm going to use this equation. So I'll write that down. So I'll have x equals h plus a times y minus k squared. Again, you could put the plus h over here, because that's how we're kind of used to looking at it. You could also make the h go over to this side, so it would be x minus h. More than welcome to rewrite it in any way that you want, as long as it's equivalent. Okay, so I'm going to look for my vertex. Let me go back to the actual image. So my vertex appears to be at -10, 3. They've given me another point as well, and that appears to be at 8, 0. Just writing those down. So now I should be good. I've got a point. I've got the vertex. I don't know what my A is. However, based on this picture, should A be positive or should A be negative? A should be positive. Okay, A should be positive. It's opening to the right, it's positive. It's opening to the left, A is going to be negative. Okay, so we're going to go ahead and calculate our A. Pretty simple problem here. You did a lot of this one when you were in Algebra 2. Alright, so I'm going to use, let's see, I've got an x of 8. I'm using this for x and y, and I'm using this for h and k. Okay? So my h is -10. I don't know what a is. That's what I'm going to have to figure out. My y is 0. My k is 3. So I've got 8 equals -10 plus, and this is going to give me 9, so I'll just call that 9a. I'll add 10 to both sides. So I get 18 equals 9a. Divide both sides by 9. A equals 2. I'm going to take that, put that back into the original equation along with my h and my k. And thank goodness A ended up being positive. It tells me that I've got the right A. So I'm going to have x equals -10 plus 2 times y minus 3 squared. And there's the equation of that parabola opening in the positive x direction.